Dear students, this video covers the unit 4 of the subject strength of materials, and this is part 2 the presentation. In this presentation we are going to discuss about the torsion equation. Yes. Before discuss about the torsion equation, we will discuss about the assumptions that we are consider the design of torsion member. The following assumptions are considered to determine the angular twist and the shear stress under the twisting moment. The first assumption is the material is homogeneous and isotropic. Homogeneous means the member is composed of same kind of material. Isotropic means the properties of the material is same in all directions. The next assumption is the plane cross section is remain plane even after deformation due to twisting moment. The cross section is remain plane. The third assumption is the twist is uniform along the length of the shaft. The twist is uniform along the length of the shaft. Due to twist, the cross-sectional fiber, that is the transverse fiber, will not get any torsion, any twist, but the longitudinal fiber will get twist. The fourth assumption is the displacement or strain at a point in the shaft is proportional to its distance from the center of the shaft. That is, the strain is proportional to its radius, right? These are the assumptions we consider in the design of torsion. Already we know the torsion equation. It is the derivation for the torsion equation. Consider a solid shaft of radius R and length L. The length of the shaft is L and the radius of the shaft is R. The shaft is considered as at one end fixed, at the other end free, that is cantilever, as shown in the figure. If the shaft is subjected to a torque T at the free end, the shaft rotates about to its longitudinal axis. This is the longitudinal axis. Because of this rotation, the longitudinal fiber will get displaced. This is known as torque. So it makes some twists to some angle. That angle of displacement of this longitudinal fiber is known as shear strain, that is pi, equal to shear strain, and is denoted by pi. This is known as pi, right? This is the longitudinal axis of on the surface, right? This is on the surface. We consider on the surface the longitudinal fiber displaced to some distance due to the twist. So the angle made, this displacement is known as pi and is called shear strain. As I already told, if there is no any clamp or fixed, it will have free rotation, the torque will not be developed. But here the one end is fixed, so it offers a resisting moment. It offers a resisting moment which is equal but in the opposite to the top. Here we apply a clockwise moment. Here we will have anti-clockwise moment. That is, here we will have anti-clockwise moment, but the magnitude is equal. This is known as torque, right? Suppose on the surface we consider a straight line AB. Where we consider? On the surface, right? It is parallel to the longitudinal axis. The dotted line refers the longitudinal axis, right? This is the longitudinal axis. A parallel line AB is considered on the surface of the shaft. Due to rotation, due to apply of this torque T, this point B displays to B dash here, right? Now the deformation, that is angle B A B dash, the angle of displacement is pi. That is, pi is nothing but shear strain. As I already told, what is pi? Pi is shear strain. Angle between B A B dash, right? B is the surface point here. Because of rotation, it displays to some distance, that is B dash. The angle between B to B dash is pi, that is shear strain. It is on the surface. Suppose if we consider the cross section, this is cross section, right? The displacement is denoted by theta. If we consider the surface, we notate the displacement, longitudinal displacement as pi, that is shear strain. When we consider the circular section, that is the cross section, the displacement by the angle is denoted by theta, right? Since the displacement is very small, right? Yes, A B B dash, is it no? B dash, right? Here the curved length is considered as straight because the displacement is very small. Now the tan pi is, what is the tan pi? Opposite side by adjacent side, that is the adjacent side is L, that is AB is L. So BB dash divided by L is pi, that is tan pi. Since the angle is, the shear strain is very small, the tan pi is equal to pi. Tan pi is considered as pi because it is very small angle, right? If the cross section is considered, the rotation is what? Theta. Therefore the arc length is, so this arc length is, what is that? R d theta, R d theta. Okay, already we know pi is BB dash by L. Here the BB dash is what? R d theta. So instead of BB dash we put R theta, that is R theta by L. It is not d theta, it is theta, right? It is theta. So R theta by L, right? Now we'll calculate the shear stress at the surface. We know the shear modulus, that is modulus of rigidity modulus, is nothing but shear stress divided by shear strain. Stress by strain is modulus, is it no? Here shear modulus, that is shear stress by shear strain. Shear stress is tau, shear strain is pi, shear modulus is G. So if you want this shear stress tau, the pi will go there, so tau is equal to g pi. Now putting this pi value here, what is that? Tau is equal to, instead of g pi, we put r theta by L. Is it now? R theta by L. So g r theta by L, the r come here. So tau by r is equal to g theta by L. This is equation number 1. Here g, that is modulus of rigidity, is constant for the material, and the theta is also a constant value. L is also a constant value. So g, theta and L, these three values are constant. So tau by r is also a constant, right? Now shear stress at the radius. When we consider the radius, what is the shear stress? For this, we consider a small strip of circle of radius small r. The thickness is dr in the circular shaft. This one, right? The shear stress will be maximum at the extreme fiber here. Maximum at the extreme fiber. This is the extreme fiber surface. But the shear stress is 0 here. 0 at the center. Shear stress is 0 at the center. Maximum at the surface, right? Shear stress due to torsion is proportional to the radial distance from the axis of the shaft. We already discussed in the assumptions. This is based on the assumption, right? Based on the assumptions, the shear stress due to torsion is proportional to the radial distance, right? So shear stress in the elemental ring is tau max by r into the radial distance small r, right? So shear stress of an elemental area is dA, right? The area of the smaller circle is dA, right? So the shear stress of an elemental area is dA. So resisting force in this elemental area against shearing. What is that shearing? What is the shearing force of that elemental area? Is stress into area. What is the stress? Shear stress. What is the area? dA. So the resisting force is tau into dA, right? So what is the resisting moment? Moment is nothing but force into perpendicular distance. Here what is the force? Shearing force. What is the distance? Radial distance. So the shear force is tau into dA, right? What is the radial distance? Small r, right? Because we consider a small strip, right? Put the tau value in this above equation. What is your tau value? Tau max by r into dA by r. Here the tau is nothing but tau max by r, right? Tau max by r into dA by r, right? So dA r into r square, right? This is for the elemental area, but for total circular bar is the total moment of resistance of the shaft, that is total torque, is tau by r into sigma dA r square. From the elementary strength of materials, we know that is sigma dA r square is nothing but J, that is polar moment of inertia. It is moment of inertia, but here we consider because of torque, so it becomes as polar moment of inertia. So tau by r into J. So T, this J comes here, so T by J is equal to tau by r. This is equation number 2. Already we have in the equation 1, that is tau by r is g theta by L. Is it no? Here tau by r is T by J. So from 1 and 2 we can write it as T by J, tau by r is equal to g theta by L. This above expression is known as torsion equation. Okay, thank you.